Welcome back to Math 104. We were looking at a scenario in a game of Deal or No Deal where you're down to 4 remaining briefcases, including your own. You've said no deal and kept playing. The next briefcase turned out to contain $1,000, so now you have to redo your expected value computation, and that means averaging up the 3 remaining dollar amounts. That average turns out to be $375,000. This is, in the mathematical sense, the expected value, the new expected value of what's in your briefcase, in light of the new information that $1,000 is no longer in contention. Even though that is mathematically the expected value, if we had the opportunity to keep playing this game over and over again indefinitely, we should never accept an offer from the banker that's less than $375,000. But if we're playing only once, and this is our one big opportunity, then it's not so obvious what to do if the banker offers $250,000. That is substantially less than the expected value, but think what you could do with $250,000. Think of the impact that would have on your life. This brings us back to a question we posed at the very beginning of the course. Which would you rather have? A guarantee of winning $100,000 or a 20% chance of winning $1 million, and why? Let's rephrase this as a choice between 2 alternatives that we will call 1A, that's the option to receive $100,000 guaranteed, and 1B, which is the option to take your chances. You'll have a 20% chance of receiving the $1 million, but an 80% chance of receiving nothing and therefore losing nothing. Which alternative do you prefer, and why? Think about this for a minute. If you ask a room full of people, you will get different replies. Some want the guaranteed $100,000 because it is a nice amount of money and it is guaranteed. But notice that from an expected value point of view, alternative 1B has an expected value that we compute as $1 million times 0.2 plus $0 times 0.8. And that is just $200,000. From an expected value point of view, it's better to hold out for the opportunity to win $1 million than to accept the guaranteed $100,000. That means that if you had the opportunity to play many times, you'd be better off taking your chances. However, if you're playing only once, then it is not obvious, and the math alone cannot tell you which is the better choice. It's very interesting to look at variations on this problem, where all that's being changed are the amounts. For example, contrast alternatives 2A and 2B. The A alternative is now to receive $1 million guaranteed, and the B alternative is to have a 20% chance of receiving $10 million instead of $1 million. The amounts in this problem are 10 times greater than the amounts in the previous version. The probabilities are the same, and when you do the expected value computation, it turns out to be $2 million instead of $200,000. So now what do you want to do? If you ask a room full of people, you will not get the same answer. You will tend to find that more people are opting for the guaranteed million in this scenario than were opting for the guaranteed $100,000 in the previous scenario. The combination of how big an impact the $1 million would have on your life, together with the fact that it's guaranteed, seem to have a strong influence on people's decision here. But there are still others who are not convinced and really do want to take a shot at the $10 million. Another variation, again where the amount that you could potentially make is 10 times greater than the amount that's guaranteed, and still a contrast between a guaranteed amount and a 20% chance of the larger amount. Now think what you'd prefer. The choices are a guaranteed $100, don't spend it all in one place, and the 20% chance of receiving $1,000. Think which one you would prefer. Now when you ask a room full of people, many of those who wanted the guaranteed 100,000 or the guaranteed million are actually willing to take their chances. Why the difference? Perhaps because $100 does not have that life-changing significance that $1 million does. If it's not going to change your life, you may as well hold out for the higher expected value, even though there's a risk of receiving nothing. As you play around with variations on this, if you find that making the guaranteed amount very large makes everyone want the guaranteed amount, and making the guaranteed amount small makes everyone want to take their chances, then somewhere in the middle it gets hard to decide. Maybe you're one of the people who finds this one a tough choice between guaranteed 10,000 and a possible 100,000, or maybe you think that it's obvious to you which one of these you would prefer. But you can make up your own version of this problem. you can make up your own version of these two amounts, where whatever the guaranteed amount is, the amount that you have a 20% chance of is 10 times greater. You can make up your own version of the numbers subject to those constraints in such a way that it really is a tough choice for you. Why are we discussing this in a probability course if the math alone is not enough to determine which decision you should make? Well, that's exactly why we're discussing it, to illustrate that the probability computation, the expected value computation, does shed some light, but it does not determine your decision. For completeness, we should really look at the other side of things. What about guaranteed versus possible losses? In alternative 5A, you're guaranteed to lose $100, and in 5B, you have a 20% chance of losing $1,000, but an 80% chance of losing nothing and gaining nothing. If you can't pay, you'll have to go into debt. Now, which alternative do you prefer and why? Think about this. When you ask a room full of people, it often happens that their intuition about losing money is different than their intuition about making money. There's something about accepting a guaranteed loss which is less attractive to many people than holding out for the possibility of not suffering any loss at all. Even though the expected loss here is $200. The expected gain is negative 200 when you do the computation. So even though the expected loss is greater, many people just dislike the idea of locking in a guaranteed loss. Again, we can play around with the dollar amounts and contrast a guaranteed loss of $10,000 with a potential loss of $100,000, and now it gets to be a harder decision. A $10,000 loss maybe you could sustain, whereas a $100,000 loss, that could be a life changer. Or maybe you'd rather take your chances and hold on to that 80% chance that you will lose nothing. The intuitions get to be difficult here. Finally, let's go back to making money. That's much more pleasant to think about. Suppose that you and 99 friends of yours are each offered a choice between two alternatives. You have the opportunity to make 100 separate, independent choices. Each friend can make their own decision. But you all agree that the total amount received by the 100 of you will be shared equally among all 100 of you. Each individual person is choosing between the guaranteed $1 million and the 20% chance of $10 million. There are 100 of you playing this game. Think, what strategy should the 100 of you use here? When it's only you, there's a strong intuition many people have that it's better to just take the guaranteed million and go home. But with 100 of you dividing up whatever you make, we see some of that long-term behavior that makes it worth basing your decision closely on expected value. If all 100 friends choose alternative 7B, it is extremely unlikely that all 100 of them will end up with nothing. If all 100 friends choose alternative 7B, and only 10 of them actually end up winning the $10 million, that's now $100 million divided among 100 people, then you're doing just as well as if you had all taken the guaranteed $1 million. And if any more than 10 of you win the $10 million, then you're doing better than if you had taken the guaranteed $1 million. Because we essentially have 100 repetitions of the game here, it's much more worthwhile to choose the alternative with the higher expected value. The intuition that it's better to take the guaranteed million, the importance of the fact that it was guaranteed, depended heavily on the idea that you were playing the game only once. With many plays of the game, it's worth taking the risk that has the higher expected value. It's worth commenting that what we've just been discussing is called prospect theory. It's a topic for which two psychologists won a Nobel Prize in economics, and the work that they did was really at the intersection of psychology, economics, and mathematics.